Now can you hear me? Oh, yeah, yeah, okay, great. Yeah, get rid of that. Is this working? Great.
Perfect. So the next talk will be given by Sam Dillavou from University of Pennsylvania, and he will be talking about analog hardware that trains itself. Please go ahead.
Awesome. So thank you for the invitation. This has been a really great conference. I've really enjoyed the conversations especially, and the talks have been awesome. Today, I'm going to tell you about this system, which I built when I was a postdoc at Penn, which I was until about a year ago. Now I'm an independent researcher working on essentially continuing the lineage of this system. So what it is a network of analog resistors that self-adjust, and then as a collective property, you get machine learning out of it. So it's an analog system that trains itself. And I'm going to argue that if we want to make precise, scalable analog computation, the best path to do it is something like this. So a system that does not require a digital model of itself to train. So let me just kind of set the stage. So if the goal is this large, or at least precise, nonlinear analog computation, why haven't we gotten there? Well, analog computers were once the dominant computing paradigm, but they stopped at about 1,000 knobs, typically less than that, because of systematic deviation. So you make a primitive like this, and you want it to do this mathematical function. It does something close to that, but it's going to depend on where it is and what the temperature is, and there are lots of little details that it starts to not quite actually do this. So when you put 1,000 of them together, you get a lot of big deviations from the overall computation. These things compound because you don't have a way to correct for errors like you do in digital. And actually, this makes even simple functions very difficult. So if you try to buy an analog multiplier that's 12-bit, you're not going to find a part that does that, right? Those have to be very specialized. So to date, as far as I'm aware, there is still no nonlinear block that's analog only that has 1,000+ tunable parameters. I would love a counterexample, but I've looked a lot. And there are a lot of things that are some of these categories, some really cool works, including some cool stuff from people here. But typically, when you have big systems, they use digital computation in line with the analog. They're integrated together, so there isn't one big analog block with that many tunable components. A lot of times you use an analog system that is not tunable at all, and what you're actually tuning is digital weights and using the analog computation along with it. Or you're doing these large matrix multiplies, but the goal is to be linear. Decades ago, there was more of an attempt at making these big analog systems, but while they may have had more than 1,000 elements, they didn't have more than 1,000 independent knobs. So this is a big goal, but it would have really big impact if we were able to do it, right? So there are a lot of places where adding software controllable, very precise analog blocks would be super useful. You could insert low power, low latency components into a lot of important places. So anything in radio frequency requires analog design, but is very difficult to do. You could also have a whole new generation of low power and precise sensing, integration, scientific instrumentation. It would be hugely impactful to do this. And so I'm going to argue that the reason that it has not been done is that the attempts all use a model. The attempts all use a digital or otherwise plan for what the components in the system are trying to do. And I'm going to make an argument that we have to remove ourselves from that, let the system do what it naturally does rather than what we want it to do in order to get the system to accomplish this goal. I'm going to make this argument probably in a kind of unexpected way. So I don't know if many of you are familiar with the bitter lesson. It's very famous in digital AI. It's a blog post by Rich Sutton in 2019. He's one of the fathers of reinforcement learning. And in this essay, this blog post, what he wrote is basically arguing that general methods that leverage computation will win eventually, because computation is getting better and better and better, cheaper and cheaper, bigger and bigger. And so if you can kind of hook yourself to that Moore's law train, you will eventually win. Okay? So in summary, kind of optimization wins at scale. And then the comparison is something like human knowledge approach that he calls it. So taking how we think a process is done in our minds or in vision, for example, and trying to give a system that knowledge directly, program it in. So picking features in an image classifier, for instance, or programming chess intuition into a chess computer. And he says basically that when you do that, you make these methods less suited to hitching onto this computation. right? You're actually kind of making a choice, and it may not be the optimal choice. In fact, it almost never is the optimal choice. And so you get in the way of the optimizer finding the optimal choice. So my rephrasing of this is that design choices are constraints, right? You're constraining your optimization space because you're picking a path, at least in part of it. And so he goes through a bunch of examples. Maybe people remember some of these where the dominant paradigm was this human knowledge approach. We're going to give this chess computer an intuition and eventually search, Deep Blue beat that. And then AlphaGo was another example where you really just let the thing play itself. You did not give it any intuition. It figured it out on its own. And that ended up completely dominating. And at the end of the essay, he says, the actual contents of minds are tremendously irredeemably complex, and we should stop trying to find simple ways to think about them, and instead we should build the meta methods that find them. So my summary of that is, messy problems may not have clean solutions. They may not be intuitive, they may not be something you can write down simply, and it may be, at scale, just impossible to write down a way, say, that your mind works. But it may be possible to find a method that figures out a very kind of inscrutable way to describe it. And this essay was written in 2019. It was before the gigantic scaling of AI, but basically this is arguing for the thing that is underlying the success of these large language models. You make these things bigger, the optimization gets better, it can do more and more impressive things. And some people take this essay to kind of mean scale is the only thing you need, and I'm not agreeing with that, but there is a kind of general approach here, which I would summarize as get out of the way, right? Choose what the system does, but don't tell it exactly how to do it. Let it figure out how to do it. Okay, so this is about digital AI. So what the heck does this have to do with my system? I would argue that this is actually a lesson we can learn in physical devices. And instead of hand-picking features in an image classifier, the design choices we're making are using models. So let me describe what I mean. So I'm going to argue that models are ultimately constraints on what the system can do. So when we design an analog, we almost always use a model. So for instance, a digital twin is a model, but also if you just write down the equation you want your circuit to do, that's a model. It's a plan, right? It's a mechanistic plan for what your circuit does, even if that mechanistic plan is found via optimization. So if I have a physical system and I want it to perform some function, and I use a model, I'm actually asking the system to do two things. I'm asking it to do this function, and I'm also asking it to satisfy the model at every level, right? So I'm asking that this resistor has a certain value because that's the way my model worked. And if you think about all the things that you have to put into a model for a physical system, which is actually very complex, you need to say, okay, sure, all the exact resistor values, that's obvious, but you also need it to match, like, if the system drifts, you need to know that. If there's nonlinearity that you weren't expecting, if there's crosstalk, if there's leakage, all of the problems that plague us as experimentalists, you need to get in the model or get them out of the experiment. And that's very, very difficult, and it gets much, much more difficult at scale. In fact, I would argue it grows, this problem, this constraint, grows faster than the system size. So when you double your system, you trivially get double the constraints, right? Okay, now there are twice as many resistors, twice as many constraints on total resistors, but you also get the combinatorial problems. So now you have new combinations of things that shouldn't talk to each other that you didn't have before. So at worst case, this is exponential. I'm not sure it's quite that bad, but in general, this constraint grows extremely rapidly with your system. And so if you go back to this picture and you say, okay, why are analog blocks still less than 1,000 knobs? I would argue it's because of this systematic deviation problem from a model. So it's not that 1,000 analog components can't do something precise, it's that we're asking them to do something very difficult, which is the thing we want them to do, and then also please match every part of our model. But if we just ask them to do the task, it's a lot easier, or it's at least a lot more feasible. So I would argue that the full power of optimization is trapped behind this simulation reality gap. And this, people know this. This is not a new statement. Simulation reality gap is a big problem. But I would argue that the solution is not to make better simulations. It's to get rid of them entirely. So just to summarize this, a digital twin or any model, to call back to the bidder lesson, dictates how the physical system performs a task. So it's a set of demands that scales with the system or even faster than the system. Makes the problem much harder. And I think shrinking the sim real gap is analogous to handpicking better features in an image classifier, getting better human knowledge into the system. So it will help, and I'm not saying simulations are useless. They're clearly very, very useful. But in analogy to this scaling argument, this is treating the symptom and not the cause. That getting better simulation models will help, but at scale, the problem still gets harder. And so I propose that instead, we optimize the physical system directly using its own responses. The system is a really great model of itself, right? And we allow components to find their own roles rather than dictating what they should be. And it's weird to think about an optimized simulation as telling the elements what job they should do, but ultimately it does, even though we as researchers are not picking what every element does. The model must match the system. So get out of the way. But I think actually analog is a really interesting place to do this because unlike in digital, I think this will have an impact even without billions of elements. And the reason is that everything's hard in analog, right? In digital, if you need to multiply two numbers, great. You can do that to infinite precision, right? As many bits as you want. But in analog, that stuff is still difficult. And so the power of optimization may be really useful even at small scales. Okay, so let's say we do this. Let's kind of ... Let's say we've done it. What does that look like? I actually think that some aspects of these systems may look a lot like biology. Now, we're not going to directly copy biology to do this, but I think kind of features of biology may pop up in our systems. So the reason I'm saying this is that biology also optimizes without pre-specifying what individual components are doing. Like pick a neuron in your head, it didn't have a predefined role in all the computations you were going to do in your entire life, right? Found that role. And we already have a precedent, right? So model-free digital learners, like large language models, feel a lot less robotic, right? Than if you remember old chatbots, they felt very, very robotic. And I think model-free physical learners can feel maybe less machine-like. So I have some specific examples there. So for instance, physical design, if you're making a machine, typically requires that you use precise components to get precise outputs. Sure. But in biology, that's not how that works. You can have unreliable components, and we do all the time. Our cells are unreliable, they die, they're noisy, and yet you get these emergently precise responses. So the ear here is indicating that if you can tell where something is coming from, then you've done a very precise timing calculation on the sounds. Design machines are often fault and damage intolerant, and obviously in biology, if that was the case, we'd be in real trouble. There's no reason this doesn't extend to other physical aspects, so mechanical aspects. So robots, right, struggle with precise manipulation and locomotion, but of course we have a million examples from people and the animal kingdom and others in life where they navigate uncertain, changing environments with grace. Now, this is a long way off. I am not going to show you a robot cat that can do flips. Far, far from it. But I think this is the vision, and I think that to get to these places, we need to move away from using a model. So just to summarize, if the goal is scalable, precise, and nonlinear analog, which I can broaden maybe even to physical computation, we must stop using design. And by that I mean compound models of the system. Because models ultimately are constraints, and they scale very badly with the size of the system. We're giving ourselves a harder problem. We're giving the system a harder problem than we need to. Okay, so with that, I'll go back to my title slide and add my subtitle, Learning to Get Out of the Way. How the heck can we do this? What's even a baby step we can take at the beginning? So I would argue that my system is one step in this direction. So let me tell you what's going on here. So my system is a network, like I said before, of analog variable resistors that we're going to train like a neural net to do functions that we want it to do. Inputs to the system are voltage boundary conditions, and outputs are measured voltages. And we're going to train the system using coupled learning, which is very, very similar to equilibrium propagation. And the way we do that is we show the system two different states, one where we let it try the problem and one where we show it the correct answer or nudge it in the correct direction. And then to adjust the system, we have knobs on each of these resistors, which are in truth MOSFET transistors with a capacitor on the gate that stores a voltage, and that's our weight. And the resistance is a nonlinear function, or a function of this gate voltage and also of these other voltages. So we can get nonlinear functionality. And the way this works, as in equilibrium propagation, right, you show the system two different states. Each edge can determine how important it is essentially in each of the two states, one where it's doing it correctly and one where it's not. And then it can determine whether it should make itself more important or less important. And it ends up, the local learning rule looks like this. So it just needs to know its voltage drop in each of the two states in order to change this weight. Okay, so hold on. I just said I didn't want to use a model, and now I'm showing you the model of my system, right? So I'm not trying to pull a fast one. What I'm saying when I say I don't have a model is I don't have a compound model. I don't have to model my entire system to know how any of my components should operate. What's being done is physics is operating my system, and my only assumption is that it's going to operate in the same way that I want it to, that power will be minimized, for instance, in my system. This is a model, and actually later we'll come back to this model being a bit of an issue. But the point I want to make is the thing that scales badly is the model of the entire system. If you model an individual component and other components are not relying on that model, it's a much easier problem to fix. Okay, so this is a schematic. This is what that actually looks like in practice, and here's the whole system. So this is the system I built at Penn. It's 32 knobs, and the way that we do the free and the clamp states is we actually have twin networks. So we run them at the same time, and then the twin edges can measure both states and update themselves. Because it's analog, it's fast and low power, and if we train it, and you can see the lights here, these correspond to the conductance or the gate voltage. When it's learning, these all adjust themselves, and then the system finds a state where it can do the task. In order to train it to do something more complex than a single data point, we just cycle between the data points rapidly, and then the system learns all of them at once. So what does that look like? So this is a readout from the experiment. This is all experimental data. Here is the task that I want the system to do. So these white dots are the labels of my data points. This is supervised learning. The line here is the output of the system. When we sweep the input, this is the output that we get. Here's the structure of the network. Here's where we're putting in the input. Here's where we're measuring the output. These are just fixed voltage boundary conditions. The width of these bars corresponds to the gate voltage. So when the gate voltage goes up, it gets more conductive, and it's like a channel widening. So you're going to see that happen. This will be a video. And I'm going to color them by whether they're shrinking or growing to make it easier to see. And these guys on the end are periodic boundary conditions. So if I cycle these data points and let the system go, this is what happens. You can see the edges are adjusting themselves based on this local rule, and the system finds a nice curve that fits the data points. Cool, so again, these edges are doing this on their own. There is no compound model of a system. I made a compound model of the system and took these weights and put it into it, and I was embarrassed at how far off it actually was from creating something like this, so I don't have it to show you, but making an accurate simulation was not part of this process. And if you look again at how this happens, how the system learns, you'll find that it actually learns these modes of error in order. So if you watch this happen, you can see first the line shifts up, and then it tilts, and then it curves. And this is similar to spectral bias in machine learning, and it's a hallmark of doing many parameter optimization in a reasonably precise way. Yeah? Yeah, so the transistor is inherently nonlinear. The idea is the conductance depends on the gate voltage, but also the other voltages it's experiencing. Yeah, great question. Okay, so here's my output. I've been talking about precise analog computation. Well, what's this then? All right, so it's not like this perfectly fits all of these data points. What about this system is not performing up to snuff? So what's limiting our optimization? So this is one of the things we looked at, because you do this, if you simulate the system, it will do a better job than the experiment, right? So it's not the sim to real gap of the whole system that's the problem, because there is no simulation. So what's still holding us back? So to look at this, we did an even simpler task. So this is just 2 data points, and we're just going to train them back and forth. So here's one input, one output, just like before, and we're going to train back and forth with some time scale tau. And if we do this in simulation, it doesn't matter what tau we pick. We always end up at a 0 error fixed point. So that the system finds the line that goes through these data points. There are many, many ways for a system this big to do this. It's not a hard problem, at least in simulation. But in experiment, when we do this, the combined error actually is strongly dependent on tau, and the floor is fine, but it's still not, 0. And if we look at this in kind of weight space, so what all the gates are doing, at the end we reach a limit cycle, and you can see that the cycle we're taking gets bigger and bigger as we do this longer and longer training loop. All right, so systems, what it's actually doing is solving one, and then it's solving the other, but it's never actually learning them both together. Okay, so in order to investigate this a little more cleanly, we made a much smaller network. So this is still experiment, but it's just 2 adjustable edges and 1 fixed edge. So the whole space of weights is 2-dimensional, so we can visualize it. And you can do the exact same problem, and you get kind of just cleaner versions of this, of these curves. Okay, so what's going on? Here's the input, here's the output. This is the space of the 2 weights. And each of these data points represents a constraint. So there'll be a line that satisfies each of these constraints, and there's 1 point that satisfies them both, which represents the line that goes through. And if you do simulation of this system, what happens is, okay, you learn task alpha, you just snap to this line, you learn this data point perfectly. Then you learn beta, alpha, beta, and eventually you get to this point. It doesn't matter where you start, you take a different path, but you'd end up there. It also doesn't matter how fast you go back and forth. Eventually you'll make it there. But if you do it in experiment, you see something a little different. You end up in these limit cycles where the system is learning one data point and then learning the other data point, back and forth. And you end up with these bow ties, as we call them. Okay, so what's going on here? It turns out that it's a sim-real gap problem, but in a kind of unexpected place. It's a local sim-real gap problem. So specifically, and not one where we really thought to look at first, it's the application of our learning rule that is imperfect. So you do things in analog, nothing is perfect. It's a lesson I've learned over and over and over again, right? So what's going on? Well, here's our learning rule, and in practice what we do is we put this into an analog multiplier and create a current that charges the capacitor. So our learning rate is kind of set by some constants and a time scale of just how long we charge the capacitor. And then the magnitude is set by this contrastive learning rule. And to leading order, we found that this was true, except there was a bias. And this bias was not something we controlled, and it was also not consistent across edges or even across experiments on one edge. If we did something very different with a network, we get a different bias. But to leading order, it was constant within one experiment. So what's the problem with this? Well, if your system is working right, you're reducing this thing to 0. Right? So your signal in a learning system, ideally, is getting very, very small because you're doing well and your error is shrinking. So what that means is you're always going to feel the effect of this bias. Even if this is very small to begin with, eventually, when this thing shrinks enough, you're going to see this effect. Okay, so I think this is a pretty broadly applicable thing in analog learning because if you can minimize your error, you're going to start seeing all the other problems that you weren't seeing before. And it turns out we can model this. There's great work done by my colleague Marcelo Guzman with a constant bias, and we get trajectories that look very similar, including when we change the time period of this oscillation. But okay, so we can model them, but the question that I'm interested in is how can we fix these problems, right? And so the answer that we came up with, which I will say is possible only because this is a local problem. So if this was a problem that was distributed across the entire network, we had to understand everything about the system in order to fix it, we would have been in trouble. But because it's extremely local, and it's not, every learning rule is not dependent on the functioning of every other element, right? We can come up with a much simpler fix for how to make this thing work. And so the fix that we came up with, if this is standard coupled learning, where we clamp the label and the signal shrinks to 0 and then this becomes dominant, is we use the exact same equation. Nothing about our actual system itself changed, just how we drive it. Instead of clamping the label or nudging towards the label, we clamp a specific amount, a set amount away from the output that we're getting now. So delta is set to be some value that makes this signal a nice magnitude. And it's called overclamping because as you get closer to the label that you want, eventually you're clamping beyond it, right? Because you're keeping that distance constant. Now that would be unstable if we just did that. So instead, what we do is we shrink the integration time proportional to the error. So the signal stays constant, but the amount of time that we apply it shrinks. And this ends up effectively being the same scaling as this over here, but you're no longer in a situation where the bias ends up dominating. How much time do I have? 5? Okay, cool. So when you do this, you can do much more complicated problems much more precisely. So here's an experiment with 100 or 200 data points. This is the readout from the experiment. You can see that it finds a nice curve here to divide these points. And I want to point out, I'll play this again, that it's doing this mode ordering thing again. So it finds a linear solution and then curves the boundary. And 200 data points matters because when you have more data points, your bias adds. So the more data points you have, the more you're kind of spreading out your error signal, but the bias is collective. And so without this technique, you have a lot of trouble doing, even say 10 data points. So this is what it looks like to try to do very simple classification problems without overclamping. And it just does not work very well. Okay, I'm going to speed through this because there's a part at the end that I want to touch on. But if you use these techniques, what you can do is train on noisy classification data, and you see double descent phenomenon. So as the ratio of parameters to data points gets bigger, the system gets worse, it hits overfitting, and then it goes down again. And this overfitting transition, as far as we're aware, has only been seen in systems where the digital part is being trained. And it's a hallmark of precise many-parameter optimization. So I think it's a sign that we're on the right track of really tuning these analog systems to do something very precise at least potentially scalable method. Okay, so like I said, for the last year, I've been working independently, and I want to just really quickly flash a couple preliminary results from that. So this is the network that I have made now. It is thankfully not all through-hole breadboards. So it's about 100 elements. Crucially, one of the changes I made is I made a single network instead of twin networks. And I was having this discussion earlier with Mark, where twin networks are, in effect, a model, right? They have to model each other. So you are, in a sense, asking something very difficult of your system, even if it's maybe a little easier to say that paired transistors do the same thing. It's ultimately still a big ask on your system. So now with a single network and just switching between these phases in time, I'm now just asking that my system be the same, say, 10 microseconds later, rather than these two big systems be the same. The edges are slightly different transistors. They're still transistors, but they are not characterized at all. The components here have a huge range in their say pinch-off voltage or ISS. So basically, using these things without characterizing them is just inviting that they will just be very different than you think they are. And I say that to point out the fact that, and this is the shape of the network, that when you do optimization with these, they can still produce extremely precise outputs. So this is 100 components with horrible tolerance, right? They could be double the number that I think they are. And I'm getting something that's over 5 bits of accuracy on the output, putting them all together. Right, so this is a simple task. This network came online a couple weeks ago. I haven't done anything super complicated with it. But the point is just to show that this emergent precision comes out when you don't have to model your system. I could not model this system. Because presumably there are things going on in here that I wouldn't have designed, but I don't have to know about them. They are baked in to my optimization. And then really cool, you can do things like kill edges. So I can turn off edges in this network and then train with this damaged network. And what you see is that the bigger your network gets, the less of a problem this becomes. In fact, it can help you sometimes. I think that's because it creates a kind of heterogeneous network that has more kind of independent knobs to play with. But you can see here, this is a 96 edge network, and until you kill more than half of its components, it works great. Okay, so let me conclude. I think physical systems are impossible to model perfectly, and this gets much worse at scale. If we want to make this goal of scalable, precise, deep, nonlinear analog, right, I think we have to remove compound models. I think they are a constraint that gets more and more difficult as we make the system better. We have to get out of the way of the system. We have to take this kind of shifting of the bitter lesson, but for us. You also have to work with your system locally, so ensuring that signal strength stays high improves the expressivity, of course, so you could get a better gradient, and doing so gives you hallmarks of precise optimization. And so you have to ask questions like, how precise do your operations need to be to succeed? So that includes measurement and application of your update rule. And how does that scale, which is an open question. And even at small scale, I would argue that these model-free systems start to look in these ways a little bit biology-like. They have these properties where the output is more precise than the components, and you can damage your system and it still functions. So that I will thank all of the wonderful people I worked with at Penn. There are a couple of papers you can check out. I don't have anything on the new network yet. And if there's just one thing you leave this talk from, it's that models are constraints.
Thank you very much, Sam, for the interesting talk and perspective. I already see multiple questions. I think you were first.
So thank you for the question.
Yeah.
Well, for the talk. You already have awesome results, but do you have any ideas what happen if you change the topology of your system, for example, make it triangle or?
Yeah. So the operation of the system wouldn't have to change. So since the elements are all local, they're doing the same thing no matter what configuration they're in.
Oh, but
right?
at least you can pack more neurons in the same area if you make it triangle.
Yeah, so that you definitely affect things like that. I'm even on PCB, right? I'm not worried about space, but ultimately that is something important, and probably the structure should take that into account. Yeah.
Right, I'm not sure who was first. I think you were, yeah?
Yes, thank you for the very interesting talk. Two quick questions. First, when you say like killing nodes of the system and it still works, you mean you do have to retrain it after you extract it?
I do. So I kill edges. My nodes don't do anything. They're just connections. But I do, yes, you're right. I do have to retrain it.
And another one, when you were showing the separation of the huge data set with 200 points, this boundary you were drawing, it had some thickness to it. Is it that
Yes.
overclamping thing? Is it proportional to that?
No. This actually is in the old system, and because of the limitations actually of this architecture, the nonlinearity was quite limited, and so this had to be really zoomed in. This whole scale is, I want to say, 10 millivolts. So it's very, very small. So this thickness comes from the fact that just the measurement precision of the devices I was using was getting worse.
You know that it says unsure. Also.
Yes, yes.
Thank
Great
you.
question.
Thanks, as usual, for the very nice talk. So I have two questions. One is, what about batching?
Mhm.
And the second, would that sort of potentially resolve this drift problem to some degree? Because you don't
What
train
drift
one-
problem?
So you
The thing that overclamping fixes?
probably not, right?
No, I think it would. I think it effectively. It doesn't change it because you're still adding those errors together too.
Still, the gradient is extremely stochastic now if you train by sample, right?
Yes, and batching is important, and that's one of the things I'm working on in the new system.
Okay.
Yeah.
And then the other question is, in principle, you could still model this, right? Because you could just make a very messy system that changes over time and whatnot. Would there be actually any benefit to building a numerical model that is like messy and then still be maybe able to analyze it?
So, like simulating a system like my system? Yeah, absolutely. I mean, I do that to figure out how to make the system better. The problem is not that you can't, that modeling a system like this is useless. It's definitely not. It's that matching that model precisely to this instantiation of the physical system is extremely difficult.
So, Dirk, and then one more question, but then we have to move on.
Just to follow up on the point here with modeling. So when you find a disagreement between the experiment and your model, you normally you would update your model.
I haven't tried that hard to make them match. I'm not claiming that someone who's better than me at it could do a good job matching at this scale. The argument is not that this system is unmodelable. It's that the problem gets harder and harder the bigger you make it, right? And so if you're trying to just close that gap, you're fighting what I think is a losing battle.
Yeah, there's a number of techniques for updating your model. one of them is, just hypothesis injection and things like this. But some interesting ones that we found useful, just for reference. I'm happy to talk offline also. Is,
Yes, please.
You can find like neural networks for the delta between the experiment and so you basically start from the symbolic model and then learn delta model. Also.
Yes.
Happy to,
yes, and I would argue that still has a scaling problem.
could well be.
Yeah.
Good.
Yeah,
Thanks
yeah.
anyways, though.
Yeah.
So.
There you go.
Hi, thanks for the great talk, Sam. One question I had was you said that you switched to the new system to, you have just one system and then you nudge it and you look at it 10 seconds later. So how do you have like a memory?
Yes.
Okay.
Yes. Yeah, you have to have a memory.
Yeah.
Yeah.
And
Of
is
some
that
sort.
like easy? Is that easy?
There are easy ways to do it. There are hard ways to do it. I'm doing what I think is a pretty easy way. It's not complicated. Yeah.